For equations like these that have more than one y per x and are not functions, it is still possible for me to get the derivatives, but there are two ways of doing it. There's the easy way, which is using implicit differentiation, and there's a hard way where I divide it up into separate functions and then I take the derivative there. So for something like the circle, I've dealt with in the past. I've known for a long time it's not a function, but I've still been able to apply a lot of the ideas that normally are only applicable for functions to it, because I'm able to divide it into two separate functions, a top half and a bottom half, and individually these things are functions. So this one isn't really so difficult to deal with. But as I get to more obscure type of functions, or functions that's just not easy to look at and tell what they look like. So something like this actually looks like this, but not that bad. It's like that. Now something like this, it's not so easy for me to divide it up into pieces. I'd have to cut it up into three pieces. I'd have to divide it into, into this part here going down, something like that, and then something like this, and then finally something like that. And it's just not that simple to get, and then I'd have to differentiate all those. So generally we like to do things the easy way, and thankfully implicit differentiation, although it sounds like it would be hard, is in fact extremely easy. It's just an application of the chain rule. So let's do one example, and after that there will be nothing to not understand. So I'll just do the first example. So if I want to differentiate this, what I'm going to do is I'm going to approach it as I would any other differentiation problem. I'm just going to start differentiating everything. Now the only difference is going to be once I get to the y, I'm going to use the chain rule. So I'm going to start differentiating everything else. So I'll get 2x, and now I get to y. The implicit differentiation is going to be using the chain rule. Basically what it's going to do is think of y squared, because if I have a normal function just like y is equal to 2x plus 1, and I take the derivative of both sides, y becomes dy dx, and this is 2. So here basically what it's going to do is say it's something like this. It's going to think of it like this. So I'm going to set this up like this. F of x is equal to, I'm just going to use u just so I don't confuse myself with the x's and y's. And then I'm going to say g of x is equal to just y. So when I use the chain rule, it's the derivative of the outside, the inside remains the same. So 2u, the inside is going to be y, so I'm going to have 2y, and then multiplied by the derivative of the inside, which is dy dx. So that's how that works. So this derivative right here is 2y dy dx, and then this is equal to 0, derivative of constant 0. So now that I've gotten this, all I'm going to do is rearrange this so this is by itself, this term is by itself, and then it will look something familiar, just like this one right here. So I'm going to subtract x to 2x over to the other side, 2y. What the hell was that? 2y dy dx equal to minus 2x divided out by 2y dy dx is equal to minus x over y. and this is the answer. This is the derivative. So it's really not that hard. It's the same as everything else. The only thing that I'm going to be doing is taking my, really, if you just want to think of it really simply, just do all the derivatives normally, and wherever there is a y, all you have to do at the end of it is just multiply a dy dx at the end of it. That's basically all that's going to happen. So you don't really, I just did all of this just to explain why that is. But really, if you just look in a book, all it's going to tell you is just tack that dy dx on the end of it. And the reason you do that is because it's using the chain rule.